Okay, this is chapter 4.4, Congruence and Transformations. The essential question is, what conjectures can you make about a figure reflected in two lines? What you will learn in this chapter is how to identify congruent figures, describe congruence transformations, and use theorems about congruent transformations. All right, identifying congruent figures. Two geometric figures are congruent figures if and only if there is a rigid motion or a composition of rigid motions that maps one of the figures onto the other. Congruent figures have the same size and shape. So looking at this first picture here, this is a quadrilateral. These are four quadrilaterals, parallelograms, or not parallelograms, but trapezoids, two parallel sides, two non-parallel sides. And when I rotate and translate and reflect, these three pieces are congruent because they're the same size and shape. But over here, we have three different triangles, and they're obviously not the same size or shape. This base here is way shorter than these two bases, and the height of this triangle is higher than these two. So these three triangles are definitely not congruent. If I moved one onto the other, it would not line up. So that is different size or shapes, not congruent. You can identify congruent figures in the coordinate plane by identifying the rigid motion or composition of rigid motions that maps one of the figures onto the other. Recall from postulate 4.1 through 4.3 and theorem 4.1 that translations, reflections, rotations, and compositions of these transformations are called rigid motions. Okay, so this is example 1, and it says to identify any congruent figures in the coordinate plane and explain. So as you can see, I have a square here, and it is called square ABCD. Now, if I took this square and moved it 1 unit to the left and 1 more unit to the left, so that's 2 units left, and 1, 2, 3, 4, 5, 6, I land right on top of triangle or square NPQR. Okay, so that is a transformation. 2 units to the left, 6 units down. So that's what you would say. So if I were to do a ray, if you will, or a vector, it would look like, try that again. Let's try this first, choose the ray. All right, and if I did a green vector, okay, so 2 units to the left, and then, what color? Blue, I guess. 6 units down, C would end up on Q, B would end up on P, D would end up at R, and A would end up at N. So what we can say here is square A, B, C, D translated two units left and 6 units down gives us square. And I'm going to name them the same. So if I name this A, B, C, D, and it's just a translation, A became N, B became P, C became Q, and D became R. So square ABCD translated 2 units left and 6 units down gives us square NPQR. Identify any congruent figures in the coordinate plane. So since this square can be translated down to a square that's the same size, that's a rigid motion, that proves the two squares are congruent. Okay, And so then we're going to continue doing this. And if we look at EFG triangle, and if I highlight my x-axis, E is 1 unit from that line of symmetry, K is 1 unit, G is 1 unit from the line of symmetry, M is 1 unit, and F is 1, 2, 3. And then if I count 1, 2, 3, that ends up being L. So triangle EFG is a reflection over the x-axis, and it yields triangle KLM. So since there is a reflection and it's the same size, so all I'd have to do is take this and flip it up, down, and move it over here and show that it's the same size, then that reflection is a rigid motion. The shapes are equal, they're the same shapes, therefore they're congruent. Okay, and I'm not going to write all that out, but that's how you would do that. And then finally, the last one, if I take this triangle here, HIJ, and I put a dot here, you can't see it now. Well, let me get rid of this, and then you can. I put a dot right at the origin. So if I rotate this, obviously I can only rotate it by that, and it keeps it in place. Okay. So actually what I could do, let me try something else so it rotates better. Okay, so I changed this so I can manipulate it better. So if I choose this triangle HIJ and I rotate it 90 degrees, it would end up here. If I rotate it 180 degrees, it would end up right there. And that is a 180-degree rotation of triangle HIJ, giving me triangle STU. They're the same size, and therefore that is a rigid motion. And that proves that they are congruent triangles. Okay, so that's how you do example 1. Okay, congruence transformations, another name for a rigid motion or a combination of rigid motions, is a congruence transformation because the pre-image and the image are congruent. The terms rigid motion and congruence transformation are interchangeable. They're synonyms. They're synonyms. So example 2 says describing a congruence transformation, and it says describe a congruence transformation that maps parallelogram, that's how you say that, parallelogram ABCD to parallelogram EFGH. So here is ABCD. Now, if I just translated that down, and let me do that. Okay, so if I thought this was just a transformation, a shift 1, 2, 3, 4, 5 left, and down 1, 2, 3, 4, you can obviously see that the red one is not sitting right on top of the green one. They're flipped over. So it is not just a transformation. We cannot just move that. If I rotated it, would that work? So let's try that. Okay, so if I wanted to rotate this, maybe I thought it was a 180-degree rotation. So I rotate it 90 degrees, I would end up over here. And if I continue down here, then there's a 180-degree rotation. But as you can see, it looks just the same as translating over and down without flipping it. So there has to be a flip involved. So that did not work. So what we're going to have to do in this situation is we're going to have to do a reflection. So if I bring this over, now let's just get rid of that. Now, if I reflect A over the y-axis, I'm 1 away. A prime is 1 away. B, if I count B, let me switch to my pen. If I count B to the line of reflection, which is the y-axis, if I count 1, 2, 3, then it's 1, 2, 3 to B prime. C is 1, 2, 3, 4. 1, 2, 3, 4 gets me to C prime, and D is 1, 2, 1, 2. So those are all going to end up an image from the pre-image from a reflection. Then if I take A and move it down 1, 2, 3, 4, I'm at E. D, move down 1, 2, 3, 4 would end up at H. B prime moved down 4 would be at F, and C prime moved down 4 would end up at G. So this would be a reflection over y-axis, okay, followed by translation down 5 units. Or is it 4? 1, 2, 3, 4. Down 4 units. Okay, so it's a reflection over the y-axis followed by a translation down 4 units. That would map A to E, B to F, C to G, and D would go to D prime and then down to H. So I wanted to point that out to you. When we are doing a transformation and we label it, when we name our transformation, the resulting pieces have to equal the congruent pieces from the image, the pre-image. So the pre-image A, which is right here, got reflected to A prime, okay? And then it got moved down 4 units to E. So A has to match with E. And notice they're the first letter in this. Then if I switch and I'm focusing on B, B got reflected over to B prime and then down to F. So B has to go with F, and so on and so on. So always make sure that your name lines up with where the pre-image vertex started and where the image vertex ended up. Okay, using theorems about congruence transformations, compositions of 2 reflections result in either a translation or a rotation. Okay, let's repeat that. Reflect and then reflect again results in either a translation or a rotation. Okay, so if we look at this diagram before I go any further, if I reflect AB over line K, I get A prime B prime. If I reflect A prime B prime over another line M, it gives me A double prime B double prime, and I could just take AB and move it over, translate it to the right, and it would land right on top of the image. So 2 reflections is equivalent to 1 translation. Okay, a composition of 2 reflections in parallel lines results in a translation as described in the following theorem. So I just mentioned that. So it says here that if line K and M are parallel, that is key, then the reflection in line K followed by a reflection in line M is the same as a translation. So if A prime is the image of A, then segment A prime, which is right here, this black segment from A to A prime, is perpendicular to lines at K and line M, and A double prime, or A double prime, the length of this segment is 2 times the distance between the 2 parallel lines. Okay, which is kind of neat. So that's what we'll be dealing with next. All right, so example 3, using reflections in parallel lines theorem. In the diagram, a reflection in line K. So let me highlight that. Let me get my highlighter. And so we're talking about try again, this right here. All right, in the diagram, a reflection in line K maps GH, this, onto G prime H prime. Okay. A reflection in line M, that's this one, maps G prime H prime onto G double prime H double prime. So we're mapping this to this and then mapping this to this in 2 reflections. Okay, we're also given that HB equals 9. So let me get my pen. So here is HB, that is 9. We're also told that DH prime, so here's D, here's H prime, that is this segment is 4. Okay, It says A, name any segments congruent to each segment. So let me say GH. Segment GH is congruent to, and here is GH. Well, when you reflect across line K, a reflection is a rigid motion, so G prime H prime is congruent. GH is also congruent to, since GH was reflected across G prime H prime, and then we reflected or across K to become G prime H prime. And G prime H prime is a reflection across line M to G double prime H double prime. Then all three of these segments are equal, so therefore G double prime H double prime segment is congruent to GH as well. Okay, so that's part of A. Now I want to know what's congruent to HB. So HB is a length of 9. Now remember, we reflected H over line K, which B is on. So the distance you reflect to the reflection is, or let me say the pre-image, the distance the pre-image is from the line of reflection, the image is going to be the same distance away. So that means that this segment is also 9, and that is segment BH prime. Okay, and then if this is 9, I guess that's all we can do for that one. I could also, let's see what else. HB, is HB congruent to anything else? Let's take a look. Okay, that's it. We can't confirm that. All right, but what we can confirm now is, since this is 4, all right, I tried to change colors. Since this is 4, and this is a reflection, this has to be 4. So H prime reflected over line M, the distance from the pre-image to the line of reflection will be equal to the distance from the line of reflection to the image. So if this is 4, this is 4. So then we can say GA, segment G, not GA. Actually, yes, we want to know what GA is congruent to. So where is GA? GA is right here. So they didn't talk about H prime D. So we want to look at GA now. Let me switch to green. GA is congruent to, well, GA is right here. And since that's a reflection, then it's going to be congruent to AG prime. Okay. So GA is congruent to AG prime. And I probably should name it the same order. GA, G prime A, since G corresponds to G prime. Let me do that. So this really should be G prime A. And when I'm thinking about that, this also should be in the right order because H corresponds to H prime. I should say H prime first. So HB, H prime B. Okay, so that's better. All right, so that's A. Now let's go on to part B. Does AC, the length of AC, equal the length of BD? That's how you say that. When there's no line over the top, you say the length of. So let me get rid of this stuff. Okay, start clean. Let me put the givens back. This is 9, this is 4. Does AC is right here, equal BD? Okay. Now keep in mind that line K is parallel to line M. So they never get closer, they never get further. And AC is perpendicular. See how this perpendicular symbol's here? These mean that that forms 90 degrees. So if, since these lines are 90 degrees, this is 90 degrees, this is 90 degrees because corresponding or same side interior angles and so on. So we form a rectangle. Opposite sides of rectangles are congruent. So AC does equal BD. I just explained it in words, but I'm not going to write it. C says, what is the length of G prime? Okay, so let me get rid of this. Where's G prime? Let me highlight it. G prime. What is the length of G prime? So here's G prime. Here's G. Okay, so in order to do this, you got to remember that HB is congruent to H prime B, which we said right here. So if HB is 9, H prime B is length 9. And since H prime D is 4, and DH prime or H double prime D was 4, okay, that was given right here, then that's a reflection. So this is also 4. So now I can find the length of this side. It's 9 plus 9 plus 4 plus 4. 9 plus 9 is 18, plus 4 is 22, plus 4 is 26. And therefore, these lengths, the total distance would be the same because this is a parallelogram. So the answer to part C is G prime, double prime. Actually, I'd say G double prime equals, no line over top, says the length of G double prime is 9 plus 9 plus 4 plus 4, which is 18 and 6, or 24 units, or actually 26. 18 and 8, sorry about that, is 26 units. Okay, so that's how you use all these theorems to prove things in diagrams. So now you should be able to do numbers 11, 12, and 14 in your exercises. Okay, so now we're on to another theorem. So it says a composition of two reflections in intersecting lines results in a rotation. So now we're not reflecting twice across parallel lines, we're reflecting twice around intersecting lines. And that does not generate a translation, it generates a rotation. So this theorem 4.3 says that reflections in intersecting lines theorem. If line K and M intersect at point P, so here's line K, here's line M, they cross or intersect at this point here, which is called P. Then a reflection in line K, this line K here, if I take AB and reflect it over here to A prime B prime, so a reflection line K followed by a reflection in line M. So if I reflect AB again over M, so AB reflects to A prime B prime, A prime B prime reflected over line M gives me A double prime B double prime. That is the same as a rotation about point P. The angle of rotation is 2x degrees, where x degrees is the measure of the acute or right angle formed by line K or M. Okay, so it's got to be acute or right, 90 degrees or less. If this angle in here, let me mark that. So they're talking about the angle that is formed by these two lines, this angle right here, that has to be 90 degrees or less. So it's 90 degrees or acute. If that's the case, you reflect it over two lines, you reflect anything over both of those lines, then the angle is going to be 2 times the angle. So if this was 46 degrees, then from here to here would be 46 times 2, or 92 degrees. Okay, so that's what we're talking about next. Okay, so here's example 4. Using the reflections in intersecting lines theorem, so line K and line M intersect at point P. Okay, that's what we're given here. In the diagram, the figure is reflected. So this blue fish, 1 fish, blue fish, 2 fish, 3 fish, something like that. This blue fish got reflected over line K and became F prime. The red fish, which is F prime, got reflected over line M and became F double prime, or the green fish. Okay, so the image is then reflected in line M. Describe a single transformation that maps F to f prime. Okay, so a single transformation that maps it. Remember that 2 reflections equals a rotation. So you could say f rotated, and it's got to look like f rotated. So it's not frotated. F rotated, and my angle of measure from the intersecting lines is 70 degrees. Remember, the theorem says that if you double that, that is the rotation angle. So fish F rotated 2 times 70 degrees. Okay, so F rotated 140 degrees. And that would be counterclockwise or CCW, but that is implied. If you don't say it, we usually go counterclockwise, or shouldn't say usually, we do. It has to say clockwise or rotated in a negative direction. This is positive. All right, so F rotated 2 times 70 degrees, F rotated 140 degrees. Would map F to F double prime. And what I should say is that it's rotated. What's the point of rotation? F rotated 140 degrees about point P. I should always say that. All right, now I'm done. Okay, this brings us to the end of chapter 4.4. Please do these exercises and more if you feel the need to practice. 35 through 43 are review from prior chapter sections. You should always practice older concepts to keep them fresh. Thanks for watching and have a great day.